Hello class, in this lecture I will talk about regression. I will mostly emphasize on multiple regression. So regression, we discussed previously simple linear regression, and the other type of regression is multiple linear regression. So usually we develop the relationship between two variables in simple linear regression. So simple linear regression, again linear is we are relating with line. So for simple we did y hat is equal to beta naught plus beta 1 x, where beta naught is your y-intercept and beta 1 is the slope. In multiple regression, so the equation would be somewhat similar. It would be the line. So in multiple regression, y hat, now we will have a y-intercept beta naught plus beta 1 x1 plus beta 2 x2 plus so on beta k xk. So this beta naught represents the y-intercept, and then this beta 1, beta 2, beta k, they represent slopes for respective variables. So that means beta 1 is slope for x1, beta 2 is slope for x2, and beta k is the slope for xk. So we discussed in these in a simple regression, if we are doing hypothesis testing, when we did for simple, we said our hypothesis would be h1 beta 1 is equal to 0. This means there is no relationship between x and y, no relationship between x and y, and then alternative is beta 1 not equal to 0. So whenever you look at this slope, this slope, if this slope becomes 0, that means there is no relationship between y and x, and if it is not equal to 0, then there is relationship, and we are trying to find the relationship. That's the main goal. So this is, there is relationship. So that is for simple. So for multiple regression, our H null would be beta 1 is equal to beta 2 is equal to beta 3 so on is equal to beta k is equal to 0. So if all these slopes, think about this, if all these slopes become 0, then there is no relationship, and then there is no equation at all, or though there is no association between different variables. So that is how you can say. And then our alternative would be at least one coefficient is different. So that means if at least one of these is not equal to 0, then that variable becomes important and we can set up a relationship. So, and then we did we did test statistic and compared it with critical value. So for simple linear regression, uh, there are two ways you can do. You looked at f, and f is greater than alpha, degree of freedom 1 and degree of freedom 2. Then you reject your null hypothesis. So that means this is not true. That means this is true. Then there is a relationship. So the other way we asked ourselves is f significance, that is what we called as p-value less than alpha, then you reject H null. So that is another way we did. So we almost in simple linear regression we relied on this, and maybe we kind of looked for the slope beta 1 p less than alpha, and we tried to reject H null, and then we said the model is significant. So that is how you will be doing this. This is simple. All this is simple. Now the same thing applies with multiple linear regressions. So let's do multiple. So in multiple, the first thing is as a whole model, as the entire model. So entire model, we wanted to make decision about the entire model. So if you look at the entire model and you are looking at test statistic value, which is f greater than f alpha, degree of freedom 1, degree of freedom 2, again this is degree of freedom of regression, which you will observe from ANOVA, and this is for error or residual. So if this is greater, again you reject H null, or again we will be relying mostly on p-value less than alpha, reject H null. If p-value turns out to be greater than alpha, you say do not reject H null. So that is how you are dealing with. So this is for p-value. This is when you look at the ANOVA table at significance, f significance they might call, or p-value they will call it. So we will look at it when we solve a problem. So for each variable, so we wanted to not only know that whether the model is good, we wanted to know about these variables. So usually let me see about these variables. Is this variable significant, or is this variable significant? So any variable that is insignificant we can throw out. So in real world, how companies manage this is like they might have 10-15 variables, and then they will throw out insignificant variables and kind of only keep the significant variables. So that's how they plan. So let's for each variable the hypothesis would be for suppose beta 1, for the variable 1 x1, hypothesis will be beta 1 is 0 and the alternative would be beta 1 not equal to 0, and then you are looking at p-value less than alpha that is reject H null. So you are rejecting H null, that means this variable is important or significant. Again you will look at beta 2 and alternative will be beta 2 is not equal to 0, p-value less than alpha. You will try to reject H null and its significance. So any variable, if its p-value is not less than alpha, that variable becomes insignificant. So on you will do until H null beta k is equal to 0. So on H alternative will be beta k not equal to 0. Again you are looking at p-value less than alpha and then reject H null, and this is significant. So you are looking at these p-values. So in most of our simple linear and all, we only deal with quantitative data. So if we have, so suppose our multiple regression equation is y hat is equal to beta naught plus beta 1 x1 plus beta 2 x2 so on until beta k xk. So we are good if all these variables are quantitative variables. You don't have to do anything. However, if any of these variables are qualitative, then you are introducing some dummy variables. So the idea is, if you have a dummy variable with C classes, so if you have a qualitative, not dummy variable, qualitative variables with C classes, you will introduce C minus 1 dummy variables. So what I am saying is, think about if I have gender. This is a qualitative variable. So this is a qualitative variable. So gender is, I have male, female. So in this case, I will be introducing, because I have two classes, 2 minus 1, 1 dummy variable. So what I mean by that is, suppose I'm trying to determine salary of based on the gender, age and years of experience. So this is x1 and this is your y variable, this is your x2 variable, and this is your x3 variable. So here I am introducing only one dummy variable because I have to introduce only one. So what this equation would look like is beta naught plus y hat is beta 1 x1 plus beta 2 x2 plus beta 3 x3, and then this dummy variable x1, because that is a qualitative variable, I will say x1 will be equivalent to 0 or 1. If you see 0, it's female, and if you see 1, it's male. So this actually leads you to two equations. This process is actually done by Excel or Minitab, but we need to understand this. So if you see, if I have a data set which has female, so that means it will put 0 at female. So y hat will become beta naught plus beta 2, because this expression is gone now, beta 2 x2 plus beta 3 x3. So this is suppose equation 1. Now if I do for male, so for male maybe I will use a different color. So for male, this expression, if you see here, I have to put 1 instead of 0, so y hat will become beta naught. So now it will be x1 is 1 beta 1 plus beta 2 x2 plus beta 3 x3. So if you see the difference, here I have only beta naught as my intercept, here I have beta naught plus beta 1. If this beta 1 is significant, so that means p-value less than alpha, then you are saying beta 1 is significant. So what it means is you will have a gender wage gap, because this beta 1 will get added into the expression, and it will kind of show you that gap in the gender wage. So that is how you kind of introduce dummy variables. So usually for qualitative variables you will introduce dummy variables. So this is how you will be doing some of these problems, but in my next lecture, this is the entire concept of multiple regression, but in my next lecture I will try to solve some problems and try to understand these concepts. Thank you.